Hello everyone, this is Professor G. Sasibhushana, Senior Professor, Department of ECE, Andhra University College of Engineering, Visakhapatnam. This lecture covers microwave components, particularly directional coupler, various applications of the directional coupler, properties of a directional coupler, principle of operation of directional coupler, and the important specifications of the directional coupler. Let us start. One of the most useful device in microcircuits and applications is the directional coupler. These directional couplers are widely used as sampling devices. What it samples is, it samples a small amount of microwave power and it gives us four important parameters. One is incident power, reflected power, VSWR, and for monitoring purposes, frequency also. And for example, this is the directional coupler 4-port device. We connect a power meter or a spectrum analyzer, etc. at one of these ports, usually at the coupled port. And from these detector or measurements, we get all these parameters. We'll see more details about this 4-port directional coupler in the coming slides. Let us see various applications of a directional coupler. First example is, let us take a radar transmitter. Look at this figure. This is a radar transmitter radiating a 40-watt power output, and this output cable is connected to the input of the antenna cable. If the characteristic impedance of the output cable matches with the input impedance of the antenna, then there won't be any reflected power from the antenna side to the source side. If there is a mismatch between the antenna cable impedance and the antenna input impedance, then there will be some reflected power flowing towards the radar transmitter side. Usually, we want to know how much power is being radiated from the antenna. Transmitter power output is 40 watt, but exactly how much power is being radiated from the antenna, every time we want to know. And what is the frequency also? Is there any reflected power also we want to know? So in this scenario, if I want to know how much power is being radiated by the antenna, this is to ensure that is exactly 40 watt, less or more power. This can be assessed by introducing a sampling device, something like directional coupler, in between the transmitter and the antenna. So let us see the figure. So this is the final system after inserting a 4-port directional coupler between radar transmitter and the antenna input side. You can see the same 4-port device I have connected here. Radar transmitter output cable is connected to the input of the directional coupler at port 1, and antenna input terminal is connected to the through port or output of the directional coupler here. We'll discuss more in detail about this directional coupler connections. And here at port 3, I will connect the spectrum analyzer or power meter, etc. for analyzing the signal or to get VSWR or reflected power, incident power if there are. The same procedure is carried on at the receiver end also, because directional coupler is used in the receiver side also. For example, base station, transmitter side, receiver side, and mobile phone also we use the directional coupler. Now let us see the basic concept of directional coupler. If you have a current carrying conductor, and if you put another conductor near to the first one, let us see what will happen. Current is flowing in the first conductor in this direction. It will induce EMF in the second conductor placed near to the first conductor. This implies that the energy passing through one conductor is coupled to the other conductor. So the induced EMF is taking place because of whenever a conductor wire is kept in changing magnetic flux, EMF is induced in that second conductor and the current is also generated. The induced EMF E equals to negative sign d phi by dt, where phi is the magnetic flux. This can be practically conceived as a 4-port device known as 4-port directional coupler. And it can be shown schematically like this, which has got 4 ports, because all the directional couplers are mostly constructed from 2 coupled transmission line set or waveguide line set or microstrips or strip lines. And it's a 2 wide, it consists of 2 waveguides and 2 holes like this. We'll discuss more in detail about this 2-hole waveguide based directional coupler in the coming slides. Here you see an input signal is divided between the coupled port and the output port like this. A small amount of the energy only passing coupled towards the port 3. Majority of the signal power is going towards the port 2. So that means we can say the coupling of signal energy from port 1 to port 3 is indicated by this arrow, and no signal or power enters into the port 4. Now let us see how a 2-hole waveguide directional coupler is made by placing one waveguide piece over the other one. This is one waveguide piece. This is another waveguide piece. I place one waveguide piece over the other one like this. The top waveguide is referred to as primary waveguide, and the bottom waveguide is referred to as secondary waveguide. In the bottom side of the primary waveguide, 2 holes are made with a distance of lambda g by 4. Similarly, the 2 holes are made with a distance of lambda g by 4 on the top side of the secondary waveguide. Finally, the two-hole waveguide directional coupler is made by placing this primary waveguide over the secondary waveguide like this. For more clarity, this figure is shown. Next we see the principle of operation of the waveguide based directional coupler. In the last slide, we have seen how a 2-hole waveguide based directional coupler is made. In this slide, we will see the principle of operation of the 2-hole waveguide based directional coupler. So this is the 2-hole waveguide based directional coupler. This is the one waveguide, bottom waveguide, and upper waveguide, which is known as the primary waveguide, secondary waveguide, which have got 2 holes on the broader dimension of the common wall, separated with a distance of lambda g by 4. So this figure shows the plane view of the 2-hole directional coupler. When an input signal enters at the port 1, it travels towards the port 2, but a part of the signal energy flows towards the secondary waveguide through the first slot as well as through the second slot. We will see more in details in the next figure. The same figure is shown for more clarity. Whenever a signal enters into the port 1, it flows towards the port 2 side, but a part of it enters through the first hole or slot, which acts like an aperture antenna, and once it enters into the secondary waveguide, it gets split into 2 parts. One part goes towards the summation port or port 3, other part moves towards the port number 4. Similarly, second signal, that is a part of the signal energy, flows towards the secondary waveguide through the second slot like this. So forward waves, there are two waves at the port 3 which are known as the forward waves, and these forward waves in the secondary waveguide are in the same phase and are added at port 3. I repeat, these two waves at port 3 which have come from first slot as well as from the second Höhler slot, and these two signals are known as the forward waves with the same phase and are getting added here because of the same phase, 90 degrees. Whereas the backward waves which are moving towards the port 4 are 180 degrees out of phase and are cancelled at port 4. So whenever a signal enters into port 1, it flows towards the port 2. A part of the signal energy moves towards the port 3, and no signals enters into the port 4 because these two signals which are arriving at port 4 are 180 degrees out of phase, so they disappear at this port. In general, 4 parameters are used to specify the performance of a directional coupler. They are coupling factor, directivity, isolation, and insertion loss. These parameters are defined in terms of power ratios. Now let us see the definitions of all these 4 parameters. The first one is coupling factor, which is equivalent to 10 logarithmic base 10 and with the power ratios of P1 and P3. Typical values of coupling factor are 6 dB. It ranges from 6 dB to 30 dB. For example, if a coupling factor of directional coupler is 6 dB, it represents the power that is available at P3 will be 6 dB down from the input power P1. Similarly, if the directional coupler has got coupling factor of 30 dB, it indicates the power that is available at P3 is 30 dB down from the input port power P1. The next parameter is directivity, 10 log base 10 P3 by P4. For an ideal directional coupler, the directivity is infinite. The third one is isolation, which is equal to 10 log base 10 power ratios of P1 and P4. Similarly, for an ideal directional coupler, infinity is defined as infinite. The last parameter is insertion loss. It is the logarithmic ratio of power ratios of P1 and P2. And these 3 parameters are related, that is coupling factor, directivity and isolation are related in terms of dB, as isolation in dB equals to directivity in dB plus coupling factor in dB. So before we finish the specifications of directional coupler, let me summarize these 4 parameters in one sentence each. Coupling factor is a measure of how much of the incident power is being sampled. I repeat, coupling factor is a measure of how much of the input power is being sampled at coupled port. Whereas directivity is a measure of how well the directional coupler is distinguishing between the forward traveling wave and reverse traveling wave. In case of isolation, it is the amount of signal separation that a device has between any 2 ports. Higher the isolation, higher the dB value, better the isolation. In case of insertion loss, it is the attenuation in the passive device when signal passes through it. So with this, we stop this lecture.